to the organizers, Indian Science Council Association, for giving me chance, and also I feel honored and privileged to deliver Dr. This is the Memorial Award lecture. My topic is a little bit different from the earlier two lectures. It is on studies on alkaline fluorphlogite and rare earth doped oxyfluorphosphate, oxyfluoride glass ceramics. So as you see here, alkaline fluorphlogite, basically I'll be discussing on that potassium fluorphlogite, barium and strontium fluorphlogite. And these fluorphlogite materials nowadays is very important as these materials are widely used for the development of the dental ceramics. And also the rare earth doped oxyfluorophosphate and oxyfluoride glass ceramics. These rare earth doped oxyfluorides or oxyfluorophosphate glass ceramics, these are also widely used for the preparations of optical devices for their wide applications of wide optical properties. And here I will specially the emphasis on that the nucleation, crystallizations, and microstructural behaviors of these fluorphogites and also that oxyfluorophosphate and oxyfluoride glass materials. Yeah, you can see that glass ceramics, these are polycrystalline ceramic material. These are produced through proper nucleation and the control crystallizations of glasses. And these fluorphlogite glass material. These are very high strength and the machinable glass ceramics. These are, as I already mentioned, is used for the wide range of industrial applications and for the developing the dental ceramics. This growth of these glass ceramics is promoted by the fluoride content as the fluoride it's entered into the glass network and it replaces the non-bridging oxygen ions and it decreases the extent of aggregations of the glass network system. Now, the rare earth drop oxyfluorides and oxyfluorophosphate glasses have drawn first attention in optoelectronics due to their wide range of optical properties. These rare earth doped glasses are widely used in optical devices such as up converters, solid state lasers, and optical fibers, etc. And among these rare earth elements, RBM3+, thulium, 3+, praseodymium, doped glass ceramics are the promising species as this glass combines the mechanical strength and the chemical resistance of aluminosilicate glasses with low photon energy. Now, the objectives of this the work. So, to develop the method for the preparations of novel high strength machinable alkaline fluorphogites and a rare earth doped oxyfluoride glass ceramics. And their studies on the nucleation, crystallizations behavior, microstructural behavior, and also the physico-mechanical behavior. Also to investigate the effects of varying on the fluoride contents on the crystallizations as well as the microstructural behavior. Also we categorize and optimize the glasses and active band concentrations by conventional spectroscopic technique like absorption, emission, also decays. Now, the machinability of the glass ceramic that basically depends on the layered structures and interlocking layered structure. Here you can see the potassium ions, the interlayer ions, and if we replace this potassium ion by means of barium or strontium, it would exhibit the better strength. And in glass ceramics, two parameters are very important. One is that hardness, and other one is the machinability. And we have to optimize these two parameters in order to get that high strength machinable glass ceramics. Now, here you can see the steps involved in the preparation of glass ceramics: the melting, the sappings, annealing, the next nucleations, the crystallizations and growth, and further test characterization. This area is particular for the glass, and this particular area is for the glass ceramics. Now, the outline of the work, first of all, that for the preparation of the different glass batches, we have to mix the different compositions of the glasses and using the attrition mill, and then transfer these glass mixtures into that platinum or platinum rhodium crucibles, and then the mixture is transferred into that high temperature furnace, and that melts at that 1500 degrees centigrade. So once the melt is completed, then the preparation of the annealing glass, and that the next steps is the it's divided into two parts, in the slab samples and the powder samples. For the powder samples, the characterizations to PTA analysis and differential thermal analysis in order to get that idea of the glass transition temperature and also the crystallization peak temperature. Now, for the slab samples, to proper nucleation and the crystallization process, the papers on the glass ceramics, and it's also divided into two parts, the slab sample and the powder samples. And the characterizations of the powder samples by XRD method to in order to get that the crystallization behavior. Now, that slab samples, again the characterizations and the density measurement, that microstructure development through SEM or TEM, and that mechanical behavior, that hardness, masonability, toughness, etc. Now here you can see that these are the different barium fluorphlogopite glass batches, and these are the compositions, and these compositions we mixed through the using these artisan mills, and after that we transferred into the platinum rhodium crucible. Similarly, these are the different strontium glass batches. Also, we have varied the fluoride content and few different batches we have prepared. Now, the once we prepared the mixtures, then we transferred the platinum rhodium crucible into the high temperature furnace, where it acts. The temperature is 500 degrees centigrade, but we that raise the temperature not in one step, but stepwise we elevated the temperature. Initially, we increased the temperature up to 900 degrees centigrade and kept at this temperature for 1 hour, and where the calcination process occurs, where all the carbon materials decompose to carbon dioxide. And then again we increase the temperature up to 1100 degrees centigrade, where all the impurities removed, and then increase 1300 degrees centigrade, and the sticky materials appeared and it starts melting. And finally, it raised 1500 degrees centigrade, where we kept the materials for 2 hours to complete the melting process. Once the melting process is over, we just remove this platinum rhodium crucible from the high temperature furnace, and then pour this into the hot iron mold to make the glass blocks. Then again we transfer the materials into the annealing furnace, where it acts at temperature 630 to 650 degrees centigrade, and kept 1 hour for followed by the natural cooling at room temperature. Now here you can see the papers of glass ceramics. After the annealing process, that the plates that we fired at 700 to 720 degrees centigrade and kept at this temperature for 2 hours to complete the nucleation process. And subsequently, we increased, heated for the different crystallization temperatures. Here you can see that 780, 850, 900, 1000, and 1100 degrees. And at every crystallization temperature, we kept the materials that for 5 hours. So these are the heat treatment schedules for the papers of the glass ceramics. Now the characterizations through differential thermal analysis. Here you can see some of the DTA thermogram for the different glass batches. Here the barium 0, barium 0.3, barium 0.5, and at different heat treatment time, and also in the range of temperature, room temperature to 1000 degrees centigrade. Here you can see for that barium 0 and barium 0.5. So there is only one exothermal peak appeared, and here the barium 0. This is due to the potassium fluorphlogite crystal phases, and here is due to the barium fluorphlogite. But for the barium point, the two exothermal peaks that appeared. First one is due to the potassium fluorphlogite, and the next one is for the barium fluorphlogite. Potassium fluorphlogite appears first due to the high ionic mobility of potassium ion due to the smaller cationic size of potassium compared to the barium. Now we just calculated that activation energy using the two equations, one the Kissinger equation, other one the Ozawa equation. Tp is the crystallization peak temperature, and beta is the heating rate, and is the activation energy. So here the crystallization peak temperatures are mentioned in these two tables for the first crystallization peak temperature and for the second one. And you can see here the crystallization peak temperature increases with increasing the heating rate, also with increasing the barium content for the two cases. And the activation energies are calculated from the slope of the Kissinger and the Ozawa plot. A very good straight lines are obtained in both the cases. The activation energies are mentioned here. The Abrahami exponents and calculated using the August-Bennett equations, and that Abrahami exponent, it indicates the nature of crystallizations of the material. And you see that if n is 2, it indicates that crystallization, surface crystallization dominates. And if it is 3, it implies the two-dimensional crystallization. And if it is 4, it indicates the three-dimensional crystallizations go to the bulk materials. Now here similarly for the strontium fluorphlogite glass batches, the detail curves. Now when we varied the fluoride for that SR0, that only one external peak appeared, and if we increase the fluoride content, the additional peak appeared, and this additional peak is due to the for the magnesium fluoride, and that with increasing the fluoride content from SR0 to SR10, both the crystallization peak temperature and the glass transition temperature both decreases, and that is towards the left. So here for the crystallization peak temperature mentioned and the acquisition energy also the free exponential factor. Here the crystallization peak temperature increases with increasing heating rate, but it decreases with increasing the fluoride contents. The N value indicates that crystallization of the glass ceramics was largely homogeneous and assuming the three-dimensional patterns of the pattern. Now we have measured the density and for the different barium fluorphlogite glass batches, and that with increasing the temperature, the density increases. It indicates that that with increasing heat temperature, that rate of formations of the barium fluorphlogite increases, and that after the certain temperature 1100 degrees centigrade, it decreases due to the partial decomposition of the barium fluorphlogite to barium aluminum silicate and the magnesium silicate. So here the density versus temperature for the different fluoride variations, and here that for a particular temperature that density increases with increasing fluoride content. For the SR5 and SR10, after the temperature 1100 degrees centigrade, it decreases due to the decomposition of the strontium fluorphlogite to strontium aluminum silicate and magnesium silicate. Now the characterizations by XRD method. So this broad spectrum indicates that amorphous nature of the glass. Now here you can see that XRDs of different barium glass batches, and now for when the barium is 0 and for the only that one major crystal phase appeared, that is due to the potassium fluorphlogite, and with increasing heat treatment temperatures, the other crystal phases appeared, that is due to the potassium aluminum silicate and also the ensetite. But for the point 3, there are two crystal phases appeared initially, and that is one is for the potassium fluorphlogite, which is the major crystal phase, and other one is for the barium fluorphlogite, which is the minor phase. This is similarly for the strontium glass batches. Now when we varied that fluoride for any particular batches, strontium fluorphlogite is the is observed at the major phase at lower heat treatment temperature, but with increasing temperature, the peaks of ensetite and the strontium aluminum silicates appear as a new phase along with the strontium fluorphlogite. And with increasing the fluorine, that the chances of the fluorine reduces the chances of the decomposition of strontium fluorphlogite to strontium aluminum silicate. Now the characteristics of the glass batches, that is the microstructural development of the glass batches by SEM or the TEM technique. Now here you can see that at that ceramized temperature 800 degrees centigrade, all that the barium glass batches, it exhibits that very fine submicron structures consist of some blocky crystals. But if you increase the temperature like 900 to 1000 degrees centigrade, it exhibits a large number of slightly bigger crystals with low aspect ratio. And further, if you increase the temperature to 1150 degrees centigrade, it exhibits a large size of the crystals with a high aspect ratio, and it indicates that as we increase the temperature, the crystal size increases, also the aspect ratio also increases. Now for this fluoride variation, the size of the crystals increases with increasing the fluorine content. For the SR0, the size is 3 to 5 micrometer. For the SR5, is 6 to 8 micrometer. For SR10, that is interlocking plate like fluorphlogite, and that size is 10 to 15 micrometer. And some cracks also have been appeared at a higher temperature as well as with a high fluorine content. And so it suggests that the fluorine promotes the crystallizations as well as the growth. So this is the EDS spectrum for the elemental analysis for these glass batches. Now the mechanical properties, that using the microhardness indenter, we have that determined that Vickers hardness, and from the Vickers hardness we have calculated the machinability and the fracture toughness. So these are the plots. the hardness versus temperature. So the hardness it decreases with increasing that the temperature due to that high rate of formation of either potassium or barium or both the potassium and barium fluorphlogite crystal phases. And after 1100 degrees centigrade, other crystal phases appeared, which is due to the instantite and that barium aluminum silicate. And for a particular temperature, with increasing barium content, the hardness increases. But the higher the hardness value, the lower is the machinability. So the fracture toughness versus temperature and also modulus. The higher the hardness, greater is the fracture toughness. Very similar, and the hardness, machinability, and the fracture toughness we found be highly dependent on the formation of the interconnected house of God microstructure. So therefore, the fluoride variation, the decrease of hardness with increasing that temperature is due to the formation of strontium fluorphlogite to a greater extent, and after this 1100 centigrade is due to the decomposition of the strontium fluorphlogite to strontium aluminum silicate and that magnesium silicate, and the machinability this increases with increasing the fluorine content in the microglass. So there are other part, that is the rare earth doped oxyfluoride glass ceramic, that nanocrystallizations of oxyfluoride glass ceramic. These are the compositions. Here you can see the X-ray diffractions. You can see here. So if we increase that time, the heat treatment time, that you can see that after 1 hour we have identified that erbium fluoride that crystal phase, and this increases with the heat treatment time. And from this, the intensity of the peak increases with increasing the heat treatment time, and that crystal size of erbium fluoride was calculated from the Square equations, and the size is ranging from 10 to 20 nanometer. Now these are the some TEM plots. The TEM and EDX analysis indicate that the phase separated droplets contains erbium fluoride, silicon, oxygen, traces of aluminium, and several erbium fluoride nanocrystals. The size 9 nanometers are formed. So these are the thermogram differential scanning calorimetric curves recorded at different heating rate, and this peaks corresponds to the erbium fluoride. And from these calculations of the Abrahami experiment from the DSC data, we found that the crystallization is by the two-dimensional mechanism, that is the nanoplates. So finally, that thulium plus iron doped oxyfluoride phosphate, we have prepared different kinds of thulium that rare earth doped oxyfluorophosphate, and this is a long chain metaphosphate glass tetraedral unit. And when the fluoride entered in this unit, that POP bonds rupture, and that it will transform into that PO3F. Here you can see IS spectrum of the oxyfluorophosphate glasses. Initially, that the metaphosphate 1260 and that's that 875, it indicates that the metaphosphate glass, but with increasing the fluorine percentage, you see metaphosphate is just removing, and that this structure of fluorophosphate glass with increasing the fluoride and the possible function of that aluminum fluoride with further increase of fluoride. These are some from the physical parameters. I will not go into details. Yeah, you can see that absorption and the emission spectrum of the glasses showing the shifting of this, the peak positions, and the fluorescence spectrum of the glass excited at 460 nanometer. The two emission band, one is that 650 nanometer, another one is the 790 nanometer. Now the conclusion: the machinability and strength can be customized by the judicious substitution of the barium and strontium or the rare earth element, and also by the time of crystallization process. So fluorine here promotes the initial crystallizations and the crystal growth, and it has an effect on the microstructure and mechanical properties. The addition of fluorine into metaphosphate glasses, it destroys the metaphosphate chain, and finally further increase of fluoride concentration leads to the formation of ALFC 3- structural element and fluoroaluminum glass. These materials would not be suitable for the industrial or the dental applications unless they are improved in crystal size and aspect ratio or reduce the hardness. So at my college, St. Mission College, Kolkata, and my collaborator Dr. Amit Mollik and Dr. Anil Kumar Barik and Professor Arnava Basu Majumdar, University of Calcutta, Dr. Paritosh Kondo, and TQ, University of Calcutta. Thank you all.
Okay.